So I'm a bit of an astrophysicist myself.
Oh, I see.
So yeah, I'm an Aquarius and my sister's a Taurus. So I'm sure you know how that goes down. Like, it's not pretty. But for some reason, I just keep dating like Sagittarius again and again. It's just not good for my chakras, you know.
I see. Well, what you're talking about is more of astrology. I am an expert in the physics part of it. I am not really an expert in astrology.
Guys, did we get the wrong expert? Like, what are we doing here? I was like wanting an astrophysicist. Like, what's happening? Anyway, so we hear about string theory and,
Yes.
you know, Einstein and
Yes.
I just really want to know, like, what kind of string is it made out of? Like, is it more of like a yarn or like a thread, or is it more hard, like copper wire?
Talking about string theory, the reason why we call them as strings because I can in a way say that these are mathematical strings. So with that inspiration,
3 hours later.
Why do they get tangled? Like, can't they just untangle them?
I think what you're trying to reach to is quantum entanglement, which is a very different phenomena than tangling of strings.
Yeah, I
That is
think I'm
more like-
really good at detangling strings. Like, I keep untangling my like headphone wires. So
Oh,
like,
that's
let me
very
know
nice.
like if you need help. in
Definitely.
your research. Dark matter.
Mhm.
Why is it dark? Did no one think of just turning on the lights? Hello and welcome back to another episode of your friendly neighborhood college counselor, bringing you insights from experts who've walked the talk. Today, we're beyond excited to have Dr. Nishil Dwivedi, PhD in theoretical nuclear physics and postdoc in quantum technologies. He's also represented India at Lindau in front of 13 Nobel laureates. Dr. Dwivedi, we're so excited to have you here today.
Hello, thank you for such a lovely introduction.
Let's learn more about your primary area of research. Tell us about what you've researched and why you were attracted to that field in the first place.
So since my childhood, what excited me with all these stories of, say, Einstein or Newton, all these physicists who were belonging to the past to the 19th, 18th, 19th century, what really excited me was that they were able to tell so much about the universe just by using a paper and a pen or just by using observation. That sort of, excited me, and that sort of idea that you can actually deduce so much about how the world works, how the universe works, how the nature works, just by, thinking about something, reading about something and writing down a few equations and making that study. That is something which really excited me since my younger age, which led me to, read more and try to learn more on physics and mathematics to actually make an attempt to understand the language of the universe. And that pursuit led me to pursue my PhD in theoretical physics, theoretical nuclear physics to be precise, where I tried to understand that how the various thermodynamic quantities can be defined for a very small particle like a nucleus. As we all know, nucleus is a very, very, very tiny particle. We all are built up of molecules, and those molecules are built of atoms, and those atoms are further, constitute of these nuclei, which have proton and neutron inside them.
Right.
So how do we actually go ahead and write a formula about them? While reading about it and while studying this during the pursuit, what I realized is that it is not a simple problem. A nucleus will behave however it has to behave, and you'll see some things in experiment and you can't really see it. So whatever assumptions you make, you spend your whole day building a theory and you write all these fancy formulas, you solve these equations, and in the end they are not going to agree with the experiments. So if they don't agree with the experiments, then whatever you have done, all this hard work, mehnat you have done is a waste, right? But it is a learning experience. So during that pursuit, what I actually found out that a nucleus is actually a chaotic system. So chaos, we all know systems which behave unpredictably. We use it in our day-to-day life, this word. But here in physics, chaos has a certain meaning. And what meaning it has is it uses certain kind of equations. There are certain kind of underlying equations to these kind of systems. So these kind of chaotic equations often arise whenever we have more than two interacting bodies talking to each other and more than two agents sort of participating in a conversation or in an interaction or in a process. And Newton was also very much aghast by this whole idea. Newton was able to say that, if I have an apple and I'm leaving it and there are just two things, one is an apple and one is an earth, and how do these two objects sort of interact with each other? Newton was very capable of deriving those equations, but there are several letters which Newton has written to his friends where he is just wondering that how things will move if I'm talking about the interaction of sun, moon and earth, and all these three gravitational fields sort of acting together. He was not able to figure it out in his lifetime.
Okay.
And even today, we haven't made too much of progress. The only progress we have made is in terms of computation. That is, we can, at every given point, we have these fancy and nice computers which we can use to calculate the trajectories at each and every point, right? And these are numerical calculations. These are not formulas. These are, if you are here, you are here, you are here, how much you are pulling, how much the sun is pulling the moon, how much the moon is pulling the sun, and how much the earth is being pulled, so on and so forth. And we do all these calculations. That is why we have got such great meteorological systems which can sort of predict and talk about climate and so on and so forth.
Can you give us some specific examples of complex systems in the real world?
Yes.
Besides the theoretical ones?
Yes. So turns out that these ideas of nuclear physics, which I was exploring, these underlying ideas of chaos are not just limited to a nucleus. Similar kind of behavior can be seen in something like traffic jams. Similar kind of behavior can be seen in how people park their cars. Similar kind of equations can sort of be seen when we see a swarm of bees moving around, or how the climate changes, or how financial markets are going up and down. All of these examples sort of highlight how complex systems and how these chaotic systems are all around us, and they sort of shape our day-to-day existence.
Okay, so what you're saying is you can actually map these chaotic situations using mathematical equations.
Exactly.
Is that correct?
Exactly.
So even the behavior of financial markets or the electricity in our grids,
yes,
they can all be modeled by using
Exactly. So if all of these, the fluctuations, you very reasonably pointed out, the electrical grids, the fluctuations which is happening in the electrical grids all over the world, they follow certain kind of underlying mathematical equations, and these things help us a lot in trying to figure out what could be the early warning signals of, say, surges, or what could be early warning signals of, say, a volcanic eruption or a landslide, so on and so forth.
Wow.
Which is very rich in mathematics.
Oh, very interesting. So can you tell us what specifically you researched on in your PhD?
Yes. So in my PhD, my first paper which was there was on the simplest three-body nucleus, which is heavy hydrogen, or also known as triton or tritium nucleus. How do we write the ground state wave functions, and how do we sort of derive those wave functions? The wave function is nothing but a fancy way of saying that there is a function which can tell you everything about that particular particle, which is something which we use when we talk about very, very small particles. So how do we find out the wave function of a simple three-body nuclear problem, and that almost exactly by writing down equations, is something which I did in my PhD. And this was one of the first part. The later parts also dealt with trying to understand how the energy levels evolve in a nucleus. So this nucleus, it has something called as discrete energy levels. Discrete energy levels is that, so I have got this cup, I can either nudge it a bit, or I can just push it and topple it over, right, like a cat. But I have this range of energies which I can provide it. But the nucleus doesn't behave this way. The nucleus, it can only have certain amounts and certain quanta of energy which it can provide or accept. Other things it will just reject. So these levels, which are discrete in nature, which are not continuous in nature, how are these levels generally distributed? What is the mathematical theory behind it? That is something which I worked on. Yeah.
Interesting. Thank you so much for sharing. So theoretical physics at times can seem very esoteric, seem very high level, abstract, and for us lay people, sometimes a little difficult to see the relevance in our day-to-day lives. So why are these mathematical formulas and equations pertinent to everyday people, and why should we care about the ongoings in this field?
This is a very, very interesting and a very relevant question. Thank you for asking this. When you ask this question, recent research or an ongoing research which comes into my mind is in the field of medical science and neurology, that of epilepsy. Epilepsy is a disease where there are certain, neural misconnections, because of which the person suffering from epilepsy can get a seizure. Now, how we generally try to cure it is that we give certain kind of anti-seizure medicines, which eventually sort of suppress the brain activity when it goes haywire. This is how it generally works. But when we look at the EEGs of the brain activity, what we see is that once the seizure is actually happening, all these brain signals, which are actually very chaotic and very, appears to be firing randomly, actually sort of synchronize with each other. And when they synchronize with each other, they lead to a seizure, right? So now what people have tried to figure it out, that since it's a problem of chaos and synchrony, it can be mapped as a chaotic problem. And if it is mapped as a chaotic problem, then what can be done is we can think about designing devices which can tune the mathematical equations in such a way by giving certain millivoltages or something to the brain, which will disturb the system altogether. So if the system gets disturbed, then your brain doesn't, synchronize, the brain waves needles don't synchronize, and then sort of you don't get a seizure.
So
it disturbs the onset of synchrony. So that is an ongoing research which can help in certain kinds of epilepsy.
That's really fascinating. So in essence, maintaining the chaos in the mind, in the brain, is what allows that person to continue to function without having seizures.
Yes, making sure that all these neurons have their different functions. If they all just start listening to each other, then they will not be doing their own functions. Right? So they have to just be independently doing their own functions.
So what appears to be random and chaotic and predictable is in essence also there is an order to that chaos. Like you can kind of map that chaos in such a way to where you sustain it.
So I like to reframe it in a different way. This entire field of nonlinear dynamics or chaos or complex systems, as I like to call it, is about trying to see that there are all these processes which may seemingly appear random, but are they actually random or are they actually chaotic? And then can we sort of study them more and try to find out the underlying equations, and then can we sort of tune them to use to our advantage. For example, here comes the work which I did in my postdoctoral fellowship. I looked at similar equations happening to a bunch of electrons or a bunch of atoms. If I have got all these bunch of atoms, can I sort of find out what are those equations which can sort of make them all synchronized with each other or make them all disassociated with each other? Can we sort of find those exact tuning parameters? If we can, then what will happen is I can over here just turn a knob in my lab and I can excite or de-excite all these bunch of electrons together. Now, why is that important? Is because of one of the most emerging fields right now is quantum computation. What does quantum computation say? It was an idea theorized by Richard Feynman, which is now actually coming into reality to a great extent these days, is that can we use these atoms or can we use these electrons or all these very, very small particles for doing computation? And if we can tame these atoms and use them in some way to do computation, there's a set way to do it. If we are able to do that, then we can achieve very efficient, very high power and very sophisticated algorithms. So what a normal computer will take billions of years to solve, it can solve it within seconds.
Wow.
So those kind of problems is something which we can address.
That is truly astounding and really awe-inspiring. So speaking of awe, as you know, I am a professional astrophysicist.
Yes.
So why is it that since time immemorial, humans have looked up to the sky for answers or have sought patterns? I mean, this is back to ancient, even prehistoric times when humans have either turned to the sky for, to think about God or about the stars, etc. And, first of all, where does this instinct come from? And number two, what can the sky tell us that is relevant to those of us on Earth?
This actually sort of ties back to the first question where I was trying to answer that why it inspired me, to take physics and theoretical physics. So what my personal understanding of this is that human beings have gone through a series of evolutions and a series of development of the brain, and then after a certain time when curiosity kicked in their brains and they started to look for stuff, they very easily realized that the questions which were unanswered were actually did not have a solution within, and they need to seek some kind of external validation. Now ground was always accessible. Humans knew how to dig the ground up, right? It was very accessible. The only thing which was inaccessible was the sky. So this is what I think, that even today, like when we are sort of trying to picture something which we do not understand, we have a tendency to look up and to wonder at the stars. I think that is the reason, because ground was always accessible to us, and then we wanted to see what's beyond it, and our curiosity at the ground level was satisfied by doing experiments and doing right and wrong things and so on and so forth. But once we look at the sky, it was absolute. It was always stable out there. It was not it was moving in a specific pattern and showed periodicity and showed beauty, to be very simply saying it. And that beauty always comes with this mystery, that what is actually making the sky that beautiful. This is actually brings me back to the first point which I said, that the initial laws about astronomy and astrophysics, say Kepler's laws, so on and so forth, were actually done by very minimal usage of very minimal tools, right? those data was just collected by staring at the night sky day in and day out by these meticulous physicists, then physicists or astronomers as we used to call them, to every single day looking at all the positions of skies every single night, looking at them, looking at the sky and noting them down, writing them down, and then trying to figure out a pattern, which data actually, with these minimalistic tools, if we look at the Kepler's 3 laws of planetary motion, which Kepler gave, even till today, the calculations and the constants which he calculated are very close, even with all these fancy telescopes which we are calculating. Very, very, very less error in that.
So of course, technology has evolved dramatically since then, and we know so much more about the planet's positioning and the stars, etc. So how does that help us again here on Earth? Of course, we are insatiably curious as a species, surely, but is there actually any relevance?
There is actually. One of the things which actually comes up in my mind is a very good blend of theoretical physics as well as a very good blend of astronomy, astrophysics. GPS is invented, and we have placed we know how to place satellites in the orbits. We place these satellites in the orbits, but once the GPS was initially invented, we could see that the location which it was pointing out was slightly off than what we could actually see where we actually were. It was not precise. Turned out that was because of certain corrections which could be done using Einstein's theory of relativity, which is a highly theoretical framework. And once people figured that out, everyone just implemented those corrections, and now in your device it is extremely precise where you are. It's like very, very precise where you are. So this is a very very nice technological revolution which happened just because of some theories which were given and all these technological revolutions which we did.
So interesting.
And it makes our life much more simpler
and
comfortable.
So I have Einstein to thank for not getting lost on my way. Wonderful. So moving on, you have given a TED Talk.
Yes.
Tell us about the topic of your TED Talk and the most interesting kind of highlights from that.
So my TED Talk was something called social physics. What social physics is for me is essentially trying to understand these complex social interactions or some kind of social phenomenon, trying to model it using a physics model. So what I essentially talked about there is social dilemma. Social dilemma is a known problem which essentially says that whenever there is a common resource which people are using, people can either be selfish and try to eat more or try to have more from the shared resource, or they can be reasonable and they can make sure that everyone gets equal share. For example, if you are going out with your friends and you guys have decided that every week you'll meet and have this party, and everyone will split the bill equally despite of whatever they order, and you go there and you see that everyone is ordering from the cheaper side of the menu, and you're like, oh, maybe I can order something from the expensive side and the load will get distributed to everyone, and you do that and you feel happy. You go home, but your friend sitting next to you also noticed that. So the next time, more and more people start ordering from the expensive side of the menu until the bill becomes too much, and one day you all have to wash dishes. And then from the week after that, you guys just stop hanging out.
No. Okay.
Yeah. So that this entire whole event. So in this case, what happened was that the personal gain was kept at a higher level than the social gain which you were actually using it for. And what ended up happening is that the social resource actually ended up getting depleted.
And what's the physics behind that?
So what we can do is we can actually model this as a bunch of bundle fibers. So if we have lots and lots of threads, and each thread is of different thickness, and all of them are kept together, and I'm putting a weight on top of it. So if I've got n amount of threads, the weight is attached to all these threads, and this weight is of some weight W. So I can say that all these threads, and the weight is distributed equally, all these threads will have the weight W upon n, correct? Very simple to understand. But the weakest thread in that would be too much strained by this force W upon n. So what will happen is that the weakest thread will break. So once the weakest thread is broken, the weight is now redistributed as W upon n minus 1. The denominator has reduced and the weight on everyone and the force on everyone has sort of increased. So what actually happens is that I can model these kind of breakdown phenomena using physics, using like a bunch of threads on which a weight is hanging, and I can sort of model it and study those equations, and the patterns which we get are something similar to, say, tax frauds, or say breakdown of a party or breakdown of a garden or
housing market. markets.
Housing markets, yes.
Yeah.
And all these things which we see in our day-to-day lives.
Okay.
Or in fact, one more beautiful example is the network ping. We all get a specific bandwidth, but when everyone is checking their exam results, then the website slows down. The reason is that everyone is sort of hogging to get that bandwidth.
Wow.
So even there, we see similar patterns.
So interesting that physics shows up in even our interpersonal and social interactions.
Yes.
So is the social dilemma entirely inevitable? Like, surely you can put fail safes in and you can put in like structures to prevent this, but is it inevitable? Will it always be the case that there's always kind of a weak link and always a rush for finite resources?
So social dilemma is very much culture dependent also.
Okay.
If there is a society in which cheating is not looked upon nicely, or in there's like say littering is not looked nicely, so even a person who litter will be looked down upon and he'll be discouraged very extensively, right? Just by the social structure we are in. So that is why the social dilemma is very much dependent on the culture. That's why building a culture is also one of the fail safes. But yes, in general, whenever there is a shared resource, this kind of problems does arise. We have seen that it does arise generally because no two people are alike, just because of the psychology and the construction of human beings.
I see. But there are certain social norms in place that have all of us kind of following them.
Correct. And that is where religion, culture, and all these things sort of help.
It serves a function in society.
It serves the function, yeah.
Everyone has certain rules that they abide by that are just commonly agreed upon.
Yes. So if you look at the original paper of a social dilemma which was written, the example which they give is of a farmland and a sheep. So if you overgraze your sheep, then other sheep will die, and then the graze land will get over and your sheep will also eventually die. So the best way to do it is either pre-decide or have a king, have a nice authoritative government who sort of decides it for you. You get this, you get this, you get this. And then that's the job of the king to sort of keep everyone happy. That's why good governments are important, and that's why government always has some or the other role to play in your life and deciding how much share you can sort of get.
I think we need these structures and rules, and as much as authority can seem didactic sometimes or dictatorial sometimes, it's also serving a very important purpose, ideally, if it's in the best interest of the people. Moving on, looking forward now to the future of the field of theoretical physics, where do you see things going in the next 10, 20, 50 years for your field?
It's a very exciting time we are in. I would say that the first revolution what happened was when electricity was sort of invented and made popularized, and then we had so many things just running on electricity. Today electricity is available. Now we are reaching to the extents and the potential of computation and of all these semiconductor chips which we are using. We are able to build amazing algorithms with machine learning and AI coming into picture, and with so much of smart design going into building these kind of computers and phones and all these amazing devices which have versatile use. We have a good amount of computation. We can now outsource a lot of calculations to the computer, which is amazing. And the other revolution which is currently happening and is on the way is that of quantum computation. So what these two fields help us in is that we can solve more and more complex problems and more complicated equations much more effectively and much more easily using these kind of resources. And in terms of quantum computation, the entire computational premise is based on some deep knowledge of physics and quantum physics and theoretical physics. So that sort of opens up a huge gate for all the theoretical physicists out there to actually build calculations, build designs, and build the right ways to actually implement their knowledge into a real world application of a device. So once this bridge happens between artificial intelligence and quantum computing, we will be having a lot of power to calculate and solve many complicated equations and many complicated features of the universe.
That's very fascinating. For students who might just be interested in getting into this field and want to foresee what kind of skills they need to prepare for down the line, what are some things they should keep in mind as they're just entering, maybe in high school or in college?
So what my general advice to students always is that read a lot, learn a lot, but always keep an application for your reading in a vision. Whatever you read, do spend 5 minutes of your time of whatever you have read today in trying to figure out that what can be a possible application of what you have learned today. In this way, you train yourself to real world problem solving. You train yourself to look at applications of things. And that is what the next generation is all about. We have a lot of resources and a lot of knowledge handy right at our fingertips these days. Now, you can't be expected to read all these books because there are way too many books now. But there are certain Bibles, there are certain relevant books which have passed the test of the time. Try to read them. Try to read as many of them as possible. And once you read them, whenever you are reading a chapter, a section, try to imagine that what could be a possible application of it. That will prepare you for because the upcoming technologies are going to be very flexible. They will be very, very versatile. We are going to focus on a lot on versatility. So since it's going to be very, very versatile, we have to be adaptive, and we need to be able to relate to various varied sections of sciences together. That kind of flexibility you should try to incubate within yourself.
So what do you think about pop culture physics? The physics that shows up in our Marvel movies or in general in science fiction? How accurate is it?
Well, many of the people do really good meticulous job in making sure that these things are pretty accurate. I just love it when I see it. Like, for example, the equations on Sheldon's boards are sometimes some kind of field equations which are actually very, very, properly accurate. The kind of experiments which they are doing in, say, Big Bang Theory, very, very accurate. For example, Christopher Nolan's movie Interstellar had a very, very good physics background. The way they visualized the black hole, they actually undertook simulations which were led by Kip Thorne. And they were, after the movie was released, they actually published a paper of it. And when the first image of the black hole was actually generated, it looked quite similar to what was actually visualized in Interstellar. And yeah, all these things are actually very, very fascinating. And sometimes it also allows us to have a scope of imagination, to think about what if. I really like watching Doctor Who. It's a British series. I just love watching it. It's all about time travel. And I'm a huge Whovian, as we call ourselves. But the reason why I watch it is because it just allows you to think about all these aspects of science and physics outside from the perspective of the current knowledge. So that really, for me, it really inspires creativity. For example, the idea of Pym particle in the Marvel movies, the idea of having some kind of, mystic element like vibranium, which can be very strong and so on and so forth. Though these are very good fiction tools, but the way they remain consistent with it throughout all these years, the way they have remained consistent with these ideas, that's really fascinating to watch. And it really, in my opinion, is really in a certain way, a scientific approach that you sort of remain consistent with the initial hypothesis which you went out. So I just enjoy it a lot, and I really love I really geek out on a very well executed from end to end. If there are physics or science concepts from end to end, very perfectly executed and staying consistent throughout the seasons, I just geek over it a lot. Yeah.
Are there any shows or movies that get the physics wrong?
Yeah. James Bond movies are a very good example. In fact, there is this professor Mithai Tulan. He has a series on YouTube which can be seen where he sort of very nicely points out, he dissects James Bond movies frame by frame and says that how by going on this ramp the car would not have made it, and he actually meticulously calculates. We can actually sit and meticulously calculate frame by frame the velocity of a car which is actually making a flip, or the velocity of a person who's actually making a flip or something, and then be like, hey, Bond would not have made it. So Bond would have all these seasons, in each movie he would have died several times, but well, he makes it
immortal.
Yeah. And of course we have some movies which defy physics on daily basis. They release very often in Bollywood. Yeah.
You're telling me the Om Shanti Ho with the tiger flying through the sky isn't on?
I have not looked at the equations though. But I do think that it can be. I think I can bet my degree on it that can be incorrect.
Okay. Thank you so much for joining us for today's episode. Fascinating conversation. So much to learn, and we look forward to having you back again for some more exciting episodes coming soon.
Definitely. Thank you very much.
If you enjoyed this video, be sure to hit like, subscribe to our channel for more such content. And before we wrap, I really want to circle back. Are you really not going to answer my question about black holes? Why just black? Why not other colors like pink, purple, green, blue? I don't know.
So the reason why black holes are called as black holes over there.
Oh, I just feel like it's not that eco-friendly. I think in 2024, we should have green.
understand.
Everyone's going green. I think we should do green.
Yeah.
Please work on that.
I'll take it up with the Ministry of Black Holes when I meet them. Yeah.